Okay, so we're still in the same section, right? There's a lot of properties here, but again, some of them, once you get used to them, are fairly intuitive, right? And this one, I think, is probably one of the more important ones. This is one you're going to use quite a lot in the homework. Okay, so let's go through it carefully, right? This is theorem 1.7, right, in the book. And it's about functions that agree almost everywhere, except maybe at one point. Okay, so we have c. Right? C is a real number, as always, right? Because x is approaching c. And we have two functions, f of x and g of x, right? And let's suppose that these functions are basically equal, right? They're essentially the same function, except at one point, except at x equals c, where they might be different. Okay, so for all x not equal to c, right, in some open interval containing c, that just means, right, near c, not too far away from c. If the limits exist, then they have to be equal, right? So in other words, even though the two functions are not equal at c, right? So it could be, let's make that clear, that it's possible that f of c and g of c could be different. They might not be equal. However, their limits are equal, right? And that's the point of the theorem, right? And that should make sense. Let's look at a graph here, right? Or let's look at two graphs. Okay, one for f, one for g. Sorry, that's not the y, that's still x. These are the y-axes. Okay, so let's start with f of x. So f of x looks like this. So it could be like a square root function of some kind, right? Let's say c is here, right? So f of c would be right about here. Right? And you can see there's no issue here. As x is approaching c, right, from both sides, left and right, y is approaching f of c. Okay? Right? Which maybe I won't even call it f of c. Let's just call it L for limit. But of course it is f of c in this case. Right. L, which is f of c here. Okay. So now let's look at g of x. G of x is going to be this function here, right? It's going to be the same, almost the same. So look what happens at c here. Now there's a hole in the graph. Okay. So as x is approaching c, from both left and right, y is approaching, it's the same L, right? It's still equal to L here. Right. But in this case, L is not g of c. Right? Why? Because g of c, of course, is undefined. Undefined. Right. Here, f of c is not undefined. Right? There's an actual point here on the graph. Whereas here, there's a hole. Okay, and I realize the arrow is not quite pointing at the hole here. So yeah, there's a hole for g. So, but notice that doesn't affect the limit. The limit is still L. Okay, so the two functions have the same limit even though they're not equal, right? F of c, is f of c, but it's not equal to g of c because g of c is, as I mentioned earlier, is undefined. Sorry about that. This g of c is undefined, whereas f of c is not. F of c is defined. Okay. So that's the idea. And again, it takes some getting used to. It might not make much sense here. But I think when we do an example, you'll see how useful this is. So I think I'm going to do an example that I left off from earlier. X approaches 0, and the function was 2x divided by x squared minus x. Right. So that was our example. We did this in the previous video, I think. Or actually, we didn't do it, right? Here's what we tried. We tried to, because this is a rational function, we tried to plug in 0 here. 2 times 0 over 0 minus 0, and we got 0 divided by 0, which of course is nonsense. That's not the answer. And so we left it at that. We said, well, we don't know what the answer is. This could be anything, right? We have no idea. All we know is that we couldn't use that particular property. I believe it was theorem 1.3? Yeah, part 2 of 1.3. So we were not able to answer that question because, of course, the denominator was 0, and that was one of the conditions, that this denominator cannot equal 0. And if it is, then it just doesn't work. We can't apply that theorem. But we can apply this one. We can apply theorem 1.7. So here's how we're going to do this, right? Here's how we're going to do this, right? We're going to think of f of x as this function, 2x over x squared minus x, okay? And yeah, we want to find the limit of that function as x approaches 0 in this case. Okay. All right. Well, something you might have noticed about this function, 2x over x squared minus x, you might have noticed that the denominator here has a factor of x in it. So you can factor out an x, multiply x times x minus 1. Right? X squared minus x is just equal to x times x minus 1. Right? So you got to get used to factoring, right? But if you notice that x divided by x is 1, right? 5 divided by 5 is 1. 2 divided by 2 is 1. So x divided by x is 1. The x's cancel. And what we end up with is 2 divided by x minus 1. Okay? That is my g of x. Okay? So notice that f of x and g of x are, well, essentially equal here. I mean, not exactly, right? But they are equal for the most part, because all I did was simplify. I factored out the x and I canceled the x, right? You're allowed to do that. However, by doing that, you are affecting the domain. The domain of f is that x cannot be 0 or 1. But for the domain of g, x could be 0. Right? It still can't be 1, but now 0 is okay. Okay? So these are equal, right, except at x equals 0. Okay, so what happens when x equals 0? F of 0, I got to scroll down a little bit. Right, f of 0 is still undefined. But what's g of 0? G of 0 is just 2 divided by 0 minus 1, which is negative 2. But negative 2 is not undefined, right? So at 0, these two functions are not equal. But that's the only place they're not equal. Right? Well, you can also say x equals 1 because they're both undefined there. But yeah, since they're both undefined, you can say that they're both, equal. But maybe not. So right. These are equal except at 0 and 1, I should say. But everywhere else, there's no problem. Right? But you can see that was the issue here. X is approaching 0, and that's the issue. So how can we find the limit? Well, here's how we find the limit. Right? We're still going to write limit. We do that at the very end. X is approaching 0. And I'm just going to simplify this function, as I did that already, right? I factor out the x. And then I can cancel the factor of x in the numerator with the factor of x in the denominator, right? So x divided by x is 1. They cancel. Right? As long as x is not 0, of course, they cancel. Right? So again, this is now your g of x, right? I simplified f of x and I got my g of x. So it's essentially the same function. But now look what I can do, right? This function here, I can plug in 0 now. Because it is a rational function. It's a polynomial, right? Divided by a polynomial. And so there's no issue, right? This is just equal to 2 divided by 0 minus 1. I don't have to write limit anymore, although I guess I could. But this is where I'm taking the limit, right? This is where I'm actually evaluating the limit. And I can do that just by plugging in 0. And you get 2 divided by negative 1, which is again negative 2. So that's the limit. That's the answer. Remember, we couldn't get it just by plugging in 0 into the original function. Right? When you plug in 0 here, you get 0 divided by 0, which could be anything, indeterminate, right? But the answer is not 0 over 0, it's negative 2. And you can get that by just doing this little bit of algebra here, a little bit of simplifying. Right? And when you do that, you get the right answer. Right? So this theorem essentially allows us to do that, right? That these two functions, I should say f and g, right? These two functions here have to be equal everywhere except possibly at c, and here our c was 0. Okay, so just make a note that this was my f of x, and after you simplify it, you get your g of x, and then you can evaluate that limit directly. In other words, just plug in the 0 here. Okay? So, so very powerful property here that it allows us to evaluate limits even when the denominator appears to be 0. The issue is, right, that the numerator is also 0. And when the numerator is also 0, very likely you should be able to simplify to get your answer. The answer here being negative 2. Okay? Now, I should warn you, of course, that this still doesn't always work. Right, so let's do another example. Well, it's the same example. Right. 2x over x squared minus x. But now x is approaching 1 instead of 0. Okay. So we can do the same thing. We can try the same thing, do the same trick. We want to evaluate the limit as x approaches 1. And I'm just going to cancel one of the factors of x here. In fact, we can do that now. I was going to do that on the next step, but we can do that now. Cancel those. And then we still have the limit as x approaches 1 of 2 over x minus 1. Okay. Well, now I can actually evaluate the limit. I can plug in x equals 1. And I get 2 divided by 1 minus 1. That's 2 divided by 0. Oops. 2 divided by 0 is not a number. It's undefined. So you can see this still didn't work here. Right? So, yeah. So again, this did not work. That's not the limit. The limit is not 2 divided by 0. It's not undefined. Okay, so now what's the answer? Well, now we kind of have to go back to the last section. What can we do? We can use a table or we can use a graph. I'm going to use a graph. So here's x equals 1, x equals 2, x equals 3, and so on. Right? So to do the graph, notice that the denominator is 0 when x equals 1. And if you remember from your pre-calc days, when the denominator is 0, x equals 1, this gives you a vertical asymptote. That's why I drew this line here, right? So the graph will look like this. It's a little sloppy, but you get the idea, right? And so the limit from the right and the limit from the left don't match. One goes to positive infinity, one goes to negative infinity. And so we give up, right? We simply say that this limit does not exist. Okay, so that's the answer. Okay. But we couldn't get that by using this property. This property still didn't work. We effectively had to use a table or a graph, either do it numerically or graphically. So again, it's always a good idea, as a fallback, when you can't do it algebraically like we did in this example. Of course, we could have done this numerically or graphically as well, but that's a bit of a pain to have to draw the graph or to make a table with all those numbers in it. But in some cases, it's necessary. Like in this case, there really was no other way to do it. Okay. On the other hand, the shortcut of it is this, right? When you see 0 divided by 0, chances are that the limit will exist. Okay. We can't say always, right? So not always, but it's a good indication that you will get an actual number for a limit. Okay. On the other hand, when you see something like 2 divided by 0, right, or negative 12 divided by 0, or any other number divided by 0 other than 0, right, that this should indicate that the limit will not exist. Does not exist, yeah. Okay, so when the numerator is not 0, yep, then you know you have a vertical asymptote and the limit will not exist, right? So yeah, so this is the case of when you have a vertical asymptote. 0 divided by 0 typically indicates a hole in the graph. Again, not necessarily, but it could. Right? It could. But when it's a non-zero number divided by 0, then you have a vertical asymptote, and then you know for sure the limit fails to exist. Okay? All right, so yeah. So again, this is a very useful property here. And again, it's just getting used to the idea of doing this little bit of algebra, right? And so what I think I'll do is I'll do a couple more examples of this where the algebra does work out here. So yeah. All right, let me write down the example here. All right, here we go. So we want to evaluate the following limit. X is approaching 3, right? And we want to find the limit of 2x squared minus 7x plus 3 all over x squared minus x minus 6. Okay. Well, look, this is a rational function. And the first thing you might try is, well, can I just plug in 3 here? So it doesn't hurt to try, right? It might work. It might not work. Right. In fact, we don't care what the numerator is. We want to make sure that the denominator is not 0. So what's the denominator? The denominator is 9 minus 3 minus 6. Right? And 9 minus 3 is 6, and 6 minus 6 is 0. So we can see right now that this is not going to work. If you did plug in the values for the numerator, you'd see the numerator would also be 0. Right? So no, unfortunately, plugging in x equals 3 did not work here. We got 0 over 0, and 0 divided by 0 is never an answer. Okay. Yeah, the last thing you want to do is say, oh, well, wait a minute, 0 divided by 0 does not exist, so the limit does not exist. That's actually incorrect. Right, so don't think that 0 divided by 0 means the answer does not exist. In fact, I just told you that when you get 0 divided by 0, the limit usually does exist, right? It's when you get, 6 divided by 0 or negative 2 divided by 0, then I think you're safe to say that the limit will not exist. But when you get 0 divided by 0, you will get a limit. So now how do we find that limit? Well, let's start by just simplifying the numerator. How do we factor the numerator? Again, you got to be experts in factoring by now, I hope. Or you can get around it by, you can use the quadratic formula and then reverse it to get the corresponding factors. But yeah, this is going to be x minus 3 times 2x, not plus 1, 2x minus 1. So 2x minus 1 times x minus 3. The denominator should be even easier. That factors as, let's see, x plus 2 times x minus 3. Yep, I think that works, right? So now you can almost see the problem here. We tried plugging in 3, and notice that this is 3 minus 3, which is 0. So you get 0 in the numerator and 0 in the denominator. And that's what went wrong, right? But now we have a common factor of x minus 3. X minus 3 divided by x minus 3 is just 1. So they cancel. And now we're left with 2x minus 1 in the numerator and x plus 2 in the denominator. Okay. So now what do? Well, this is a rational expression, a rational function. We can try plugging in 3 now. 2 times 3 minus 1 divided by 3 plus 2. So 2 times 3 is 6, and 6 minus 1 is 5, and 3 plus 2 is also 5, right? So we get 5 divided by 5, so we get a limit of 1. Okay. So yeah, in this case, 0 divided by 0 was 1, but again, you don't know that from 0 divided by 0, right? Or 6 divided by 0, or negative 2 divided by 0, right? So yeah, the limit here was 1. Right? And you do it just by simplifying, right? Simplify the expression, and then you can plug in the number. Right? Relating it to the theorem, right? This function up here, that was my f of x, right? This function down here, this is my g of x. And they're the same function. These are equal, right? Except at x equals 3. That's the very value that we wanted to find the limit for, right? As x approaches 3. Okay, so that's why this did not work up here, and it did work down here. We had to simplify first to get your g of x, and then just plug in the 3 into your g of x. Okay, oh, I'm running out of space, so let's do another one. Okay, here's our next example. We want to evaluate the limit as x approaches 6 of the square root of x plus 10, and then minus 4 outside the square root, and then all of that divided by x minus 6. Okay, so that's the problem. And, well, the first thing you might try is plugging in 6, but I think you'll see very quickly that that's not going to work because the denominator is 0. Okay. Now, it might help to figure out the numerator as well. The numerator is, let's see, the square root of 6 plus 10 minus 4, so that's the square root of 16 minus 4, but the square root of 16 is 4. 4 minus 4 is 0. So we do get, again, 0 divided by 0, which could be anything, right? So, no, this did not work, right? Plugging in 6 didn't work, right? Sometimes it does, but in this case, no. So, now what do we do? Well, so I'm just going to copy the problem down again. And we have to simplify this function, right? The square root of x plus 10 minus 4 all over x minus 6. So how do I this, right? Well, it's an issue of factoring, right? But it doesn't look like we can factor this, right? Because it's not a polynomial. Yeah, it's not a polynomial. So unfortunately, this involves a little bit of a trick here. One that you've done before, maybe, I hope. Well, actually, we did talk about rationalizing the denominator. This is the exact opposite. Here we're going to rationalize the numerator. Weird, right? In your algebra days, they always say rationalize the denominator. Here it's the opposite. Here we want to rationalize the numerator, not the denominator. Okay, and here's how we do it. We're going to multiply top and bottom by the same thing. So we're just multiplying by 1, right? But in this case, we're going to multiply by the conjugate of the numerator. It's not the square root of x plus 10 minus 4, right? It has to be the opposite sign here, plus 4. And then do the same thing in the denominator, plus 4. And again, all of this is just equal to 1. I can cancel it and go back to the beginning. But then you're just back to square 1 again, right? Oh, sorry about that. So, so how does that help? Well, let's multiply this out in the numerator, right? We still have to take the limit. So yeah, you have to keep writing limit here, right? That's crucial. If you stop writing limit, then I'm assuming that's when you're taking the limit. We usually don't do this until the very, very end. Okay, so yeah, you can lose points if you just stop writing the limit. So I know that's irritating, but we didn't take the limit yet. We do that at the very, very end. Okay, so let's multiply this out, right? We're just going to use FOIL here. The square root of x plus 10 times the square root of x plus 10 is just x plus 10, right? The square roots cancel. And then for the outside, we're going to get plus 4 times the square root of x plus 10. And then the inside, we're going to get negative 4 times the square root of x plus 10. So now you see why we needed the plus instead of the minus. Because if this were a minus, these wouldn't cancel, right? These would combine, and you would get negative 8 times the square root of x plus 10. But as it is, these two things right here just add up to 0. That's what we wanted to have happen, right? Oh, don't forget the last two terms. The negative 4 times the positive 4 is negative 16. So we still have that. What about the denominator? The denominator is x minus 6 times the square root of x plus 10 plus 4. If you're wondering, why didn't I multiply this out, right? Why didn't I do FOIL here? Well, we could, but you're missing the point. You don't want to do that for the denominator. You want to leave the denominator alone. Okay? It's the numerator you have to multiply out, right? And we already said that this just adds up to 0. So look at what happens to the numerator now. Oops, sorry. That's supposed to be a 6. X is approaching 6. So the numerator is just x plus 10 minus 16. And the denominator, again, do not multiply this out. We're going to leave it alone. And you can see the only thing we have to do in the numerator is take 10 minus 16. 10 minus 16 is just negative 6. So now we still have to find the limit as x approaches 6 of x minus 6 divided by x minus 6 times the square root of x plus 10 and then plus 4. Now you see why we did all this, right? This is just x minus 6 times 1. The 1 is usually invisible, but it's always there. And now you can see what happens. We can cancel x minus 6. It's a common factor in the numerator and denominator. All right. And when we do that, well, we're almost done. So we still have to take the limit as x approaches 6 of 1 over the square root of x plus 10 and then plus 4. Right? We canceled the x minus 6's. So now there's no issue. Now you can plug in 6. You get 1 over the square root of 6 plus 10 and then plus 4. And now I need a little more space here. So this is going to be 1 over the square root of 16 plus 4. The square root of 16 is 4. And 4 plus 4 is 8. So we get 1 over 8. And there's our answer. If you like decimals, then you can write 0.125. I prefer the fraction, but I'm not picky about it. You can write it either way. But that's it, right? So this limit was 1 over 8. And let me erase all this. Well, let me just cut it. Yeah, it takes me a little more time to do that. But yeah, so the answer here was 1 over 8, which of course is not equal to 0 divided by 0. So yeah, a bit of a pain to have to simplify this. You have to rationalize the numerator instead of the denominator, right? So yes, you have a square root in the denominator, right down here, which again, in the old days, they always say that's not allowed. Well, here, we don't have a choice, because the only way to do it is to put the square root into the denominator. In the end, of course, the square root of 16 was just 4, so there's no square root in the end. But, you know, there could be in other problems, but not in this one. Yeah, so that's how to do this. Again, when you see square roots, typically you might have to rationalize the numerator. So just be aware of that. I think I'll do one more. That's because you might see this in the homework. Okay, so we want to evaluate the following limits. The limit, as this is a Greek letter delta, so delta x approaches 0 of the function x plus delta x quantity cubed minus x cubed all over delta x. Okay, so this is a little different than the ones we've been doing. This is more of an algebra problem because, right, it's x is not the, right, this is not x approaching 0. Don't get confused by that, right? X and delta x are two different things, right? X and delta x are two distinct variables. Okay. And in fact, we don't have to call it delta x. Your pre-calculus book might have called it h. So we could use an h here instead of delta x, but this book tends to use delta x. And so that's what I'm going to stick with here, is delta x. But if you want to just change it to an h, that's fine. But I'm not going to do that. All right. So how do we do this, right? Well, first thing you can try is just plugging in delta x equals 0, but of course delta x is the denominator, so the denominator would be 0. And of course the numerator would be x cubed minus x cubed, which is also 0. So you would get 0 divided by 0 again, and as we all know, that's, well, we know by now that that's just not an answer. Right, this 0 divided by 0 is indeterminate. Okay, we cannot determine it just by looking at 0 divided by 0. Okay, no idea what it is like that. So what are we going to do here? Well, we're going to simplify. Right, we're going to take limit as delta x goes to 0, and I'm just going to expand this out here. This is going to be x plus delta x times x plus delta x times x plus delta x, right? Because it's to the power 3, it's 3 of them. And then minus x cubed, all over delta x. Oops, delta x goes to 0, so we still have to take the limit. And this is where it's very helpful if you know the binomial theorem. We do that back in college algebra. If you take college algebra, that's a typical application that we do at the very end of the course. If you don't know it, well, it's a little bit worse. It's a lot of algebra. So I'm not going to do the binomial theorem, as it turns out. I'm just going to multiply this out. And we just use FOIL here, right? Multiply this out, and what you're going to get is x squared, right, plus x delta x plus another x delta x. So that's 2x delta x plus delta x times delta x is delta x squared. Okay. So, yeah, so that's the numerator here. X squared plus 2x delta x plus delta x squared. And then we still have to multiply by another x plus delta x. Just very tedious. Just very tedious here. Okay, so we still have to take the limit. Delta x goes to 0. We still have this one big fraction, right? And now let's see if we can do this. We're going to do x squared times x. Of course, that's just x cubed. And then we're going to do x squared times delta x. And then we're going to do, let's see, 2x delta x times x, which is 2x squared times delta. Oh, I was going to do this all at once. Shoot. Okay, so 2x squared times delta x. And then we multiply 2x delta x times another delta x. So I guess that's going to be 2x times delta x squared. And then we have the last term here, delta x squared times x. So I'll put the x in front. This is just x times delta x squared. And then finally, we have delta x squared times delta x. That's just delta x cubed. And then don't forget the minus x cubed here at the very end, all divided by delta x. Yeah, a lot of algebra. Again, this would have been a lot faster had we done the binomial theorem. But since I'm not assuming you know what that is, it's just very tedious. Okay, but we can simplify this, right? This is going to be 1x squared delta x plus 2x squared delta x. These are like terms. 1 plus 2 is 3, so you're just going to get 3x squared delta x. Right, so still write the limit. We didn't take the limit yet. That comes much later. Okay, we still have x cubed in front, and now 1x squared delta x plus 2x squared delta x is 3x squared delta x. And it turns out that these two expressions here are also like terms. We have 2x delta x squared plus 1x delta x squared. So that's going to give us 3x times delta x squared. Plus another delta x cubed, and then minus x cubed. Right, so this is looking a lot better. Okay, but we're still not done yet. Okay, so what can we do? If you notice, we have x cubed minus x cubed. Well, that's just 0. Right? That just adds up to 0, so these cancel. Now, every other term that's in the numerator has this delta x in it. It's a common factor. So we can factor out the delta x and multiply by, let's see, 3x squared, right, times 1, plus 3x times delta x, plus, and then delta x squared, all divided by delta x. Okay. Well, there you go, right? This is just delta x times 1. This is delta x times all of this. Delta x divided by delta x is 1. So they cancel. And then this divided by 1, so you just end up with 3x squared plus 3x times delta x plus delta x squared. Okay, well, now there's no issue, right? Up until now, we had this delta x in the denominator. See that? And that was the big problem, because when delta x is in the denominator, you're dividing by 0. See that? But now there's no more delta x in the denominator. In fact, the denominator is just 1. You can always write it over 1 if you want, but not necessary. So now just take the limit, right? In other words, everywhere you see a delta x, just change that to 0. So this is 0, and this is 0. So we end up with 3x squared plus 3x times 0 plus 0 squared. Well, 0 times 0 is 0. 3x times 0 is 0. So this is 3x squared plus 0 plus 0. In other words, you just get 3x squared. And that's the answer. So remember, that was the original question. Whoa, way up here. Yeah, so this limit up here is just 3x squared. I'm going to squeeze that in there. But we couldn't find it just by plugging in delta x equals 0. At least not initially. We had to do all this algebra, all this horrendous algebra here. Once we simplify it to this, right, we got rid of that delta x in the denominator, then there's no issue. Then just let delta x equal 0 here. And we get our final answer, 3x squared, right? And maybe for some of you, without realizing it, we just calculated our first derivative. So this entire process, right, as horrendous as it might seem, is a very important process here. It's something that's going to come up in the next chapter when we talk about derivatives. How you find a derivative is, well, the way what we just did. And you might think, oh no, if the entire course is like this, if finding derivatives means we have to do this all the time, I don't know if I like this, right? So that seems like bad news here, right? That if we're going to do this a lot, this is going to be just awfully tedious. So there's some good news here. You don't have to do this a lot. We will be doing this more a little bit. Maybe half a dozen more times. Okay, or maybe a dozen more times. That's maybe not quite that many. But 5 times, 6 times. Once we get used to this process here, sorry I keep going back and forth, you must be dizzy by now. But once we get used to this process, finding these types of limits here involves something called a derivative. And we're going to do a lot of that later. Not necessarily by using limits, but by using shortcuts, by using rules. Okay. In any event, right, if you don't know what a derivative is, that's fine. We're going to do that later. But that's what we just did, right, without even realizing it. Well, some of you probably knew this, but most of you probably had no idea. In any event, yeah, so that's why finding limits is important. We're going to be using derivatives, and derivatives have to do with rates of change and tangent lines and all that. Okay. All right, so that was a long one. So, but we're not done. I'm just taking a short break here while you kind of absorb all this algebra here. I hope it wasn't too sloppy. But we're gonna have to do a couple more properties here, and so I'm gonna erase all this and start over. Okay, so 2 more properties here. Theorem 1.8 is called the Squeeze Theorem. So when a theorem has a name like the Squeeze Theorem, that typically means it's kind of important. Usually, it's the name of the person who either came up with it, invented it, or proved it. Although not necessarily. But there's no name here. This is just a description of the theorem. Some books call this the sandwich theorem. I like Squeeze Theorem better, actually. So that's the Squeeze Theorem. And here's what it says. We have 3 functions, h, f, and g, all in that order, right? So h of x is less than or equal to f of x, and f of x is less than or equal to g of x. For all x on some open interval containing c. So somewhere near c, right? Near c. But this doesn't have to be true at c, just near c, right? Or sometimes this open interval containing c, you can also say, right, in a neighborhood of c. So neighborhood is a mathematical term, actually. It just means nearby, in a neighborhood of c. All right. So if the following limit holds, so I'm going to take the limit as x approaches c of f of x, or sorry, h of x. And let's say we get an answer. Let's say it's equal to L. And let's say that happens to be the same limit for g of x. Well, in that case, we have to conclude that the limit as x approaches c of f of x also has to be equal to L. Right? And that kind of makes sense, right? If this is approaching L and this is approaching L, well, f of x is in between. So it has to approach L also. Right? And so maybe a graph would help here. So let's draw a graph of three functions, all on the same xy plane here. So h is the smallest function, so h might be this function here. So this is h of x. I'm going to draw g of x is the biggest function, so that might be this function up here. So this is g of x. And then f of x will be somewhere in the middle, right? And you can see it's got to be squeezed in between, so it's got to do this. Okay, so that's f of x. Right, and you can guess what c is. C is going to be right here, where they all kind of converge. Okay. So, yeah, so what happens as x approaches c from the left and from the right? Well, h of x, right, approaches this y value here. I'll call it L. And g of x also approaches L. Well, that forces f of x to also approach L as well, because the function f, the graph is squeezed in between g and h. Okay, so that should make sense then, right? So that might help explain this squeeze theorem up here, right? You're squeezing one function, f, in between two other functions that have the same limit. And so f has to have the same limit as well. Okay. All right. So one reason for giving this theorem, and this is going to come up, a couple of times later on. And it's going to come up again in Calc 2 as well. But it does come up immediately if you want to prove these two theorems, these two properties here. So the next property are these two right here. But I'm not gonna prove these, not using the squeeze theorem. Okay, so these are just two limits that you should know by heart because they're going to be needed later on. They're just going to come up again. Okay, so I'll write them down again so we know. Right, so the first one is that the limit as x approaches 0, right, of sine of x divided by x, that limit is 1. Okay. You might have actually seen this already. You might have done this, I think, in the, I think it was section 1.2. It was in an earlier homework where they wanted you to do this numerically, right? Plug in values of x that are close to 0. Actually, I think I did this one. If I remember right, I think I did one. Either one like this, similar to this, or this very one. Yeah, but so either way, the answer is 1, right? So doing this numerically should make sense. You get an answer of 1. And I remember doing it using a graph as well. And we got the same answer. Okay. But the point is, we could use the squeeze theorem up here to prove this algebraically or geometrically. It's in the book. If you're very curious, you can look at it. But this video is already going way long. So I think I'll leave it at that. The other one is this. X approaches 0 again of 1 minus the cosine of x all over x is equal to 0. Okay, so this is one you should be able to do numerically or using a graph. I don't know how to use the squeeze theorem directly to do this. I think there's another way to do this algebraically. And possibly using the... Actually, I think it might be a homework problem, so I don't want to say too much more. If it is for homework, or if you want a challenge, if you want to do this, here's a hint. Use the conjugate. Right, the conjugate of the numerator is 1 plus cosine x. And you might want to multiply and divide by 1 plus cosine x. And I think that will give you, you go through the algebra, and I think that'll give you the answer 0 here. Okay, so it's a good exercise to go through. It's just more algebra and a little bit of trigonometry, but I think you can handle that. Okay, but I do want to do some further examples of number 1, because sometimes it's not always going to be clear here. Suppose we want to take the limit as x approaches 0 of, let's do the sine of 4x divided by the sine of 7x. Okay? Yeah, so a little bit of a tricky one. Now, so you might say, well, wait a minute, this is sine divided by sine. It's not sine of x divided by x. So no, it's a little different than this. But to do it algebraically, we're going to essentially use this up here, right? It's the fact that this limit is 1 to help us out here. But we got to do a little bit of algebra first, right? Now, what you don't want to do is say this. Well, look, x divided by x is 1. They cancel. Sine divided by sine is 1. They cancel. And the answer is 4 over 7. And that's wrong. You cannot do that, right? It's very bad. It's usually going to give you the wrong answer. Unfortunately, it does give you the correct answer, but for the wrong reason, right? After all, you can't just cancel the x's here, because then your answer wouldn't be 1. Your answer would be sine. But that's nonsense, right? Sine of what, right? You cannot cancel the x's here. And so for that matter, I erased the parentheses here. Yeah, you cannot cancel sine. You cannot cancel the x. It doesn't work. Okay, so what does work is the following. So I'm going to split this apart, right? I'm going to write this as the sine of 4x divided by 1 times 1 divided by the sine of 7x. Okay? So if you multiply these two fractions, right, you just get this again. It's the same thing. Right? Now what? Well, notice that there's a blank down here. There's a 1, of course, but what I need is the same angle in the numerator as in the denominator. I need the x, right? But notice, I'm not taking the sine of x, I'm taking the sine of 4x. So I also need a 4 here. Okay? Now keep in mind that I just divided this whole thing by 4x. That wasn't there before. So what do I have to do? I have to multiply also by 4x. Actually, before I do that, just keep in mind the 4 is still here, right? 4 is still here. But we're going to do the same thing over here. We're going to put the 7x, in the numerator here, right? To match the 7x in the denominator. Okay, so what I multiplied by was x divided by x. X divided by x is 1. So I can always multiply and divide by x. But I cannot multiply by 7 over 4 unless I multiply by 4 over 7. Right? So this 4 cancels this 4, this 7 cancels this 7, and now we just multiplied by 1. Okay? So, yeah. So all that sets us up for the following. Right? So first thing I'm going to do is just pull this 4 over 7. It's a constant. I can pull that in front of the limit. Remember, constants can go in front of the limits. Right? And now I just have the sine of 4x divided by 4x times, well, 7x divided by sine of 7x. But this is really just the limit as x approaches 0 of 7x divided by the sine of 7x. Right? You're just multiplying. Remember, the limit of a product is the product of the limits. Right? That was one of the earlier rules we talked about. It seems like a long time ago now, right? Okay. Well, this is still 4 over 7. This limit here you should recognize. Right? It's the same as this. Now you might say, wait a minute, it's 4x and not x. Whether I call it x or 4x doesn't matter. Right? It still goes to 0. Right? If x goes to 0, 2 times x goes to 0. 3 times x goes to 0. 4 times x goes to 0. So, yeah, again, if that bothers you, then just put a 4x here. 4x goes to 0 instead of just x goes to 0. Right? But yeah, if x goes to 0, if x is approaching 0, right, 2 times x is also approaching 0. 3 times x is approaching 0. 4 times x is approaching 0. 99 times x is approaching 0. Right? Right? Maybe not as fast as x, but it still approaches 0. Right? You know, if you plug in a small number here for x, like 0.00001, then 99 times that, well, it's still not as close to 0, but it's still close to 0. It's just not as close, right? So the point is that all of this limit here, right, is just 1. And the same thing here. This is also 1. So the answer is 4 over 7. Right? Now, earlier I might have said, wait a minute, that's wrong. I didn't mean it was wrong. I meant that you cannot take the shortcut here. You cannot just cancel the signs and the x's and end up with 4 over 7. I mean, you know, I guess it works, right? You get the right answer, but for the wrong reason. And if you do this all the time, you're really going to end up in trouble, because most of the time this doesn't work. This usually gives you nonsense or incorrect answers. Okay? So it's really a bad habit if you do it that way. And if you do it that way on a test, well, you know, you might get a point for the right answer, but you're going to lose a lot of credit for just not knowing the proper method here. Okay? So this little bit of algebra here, and I realize it's kind of a trick, it's a technique you got to get used to. This is the way to get the right answer. Split it up, multiply top and bottom by x, multiply top and bottom by 7, and then top and bottom by 4. So in the end, everything we multiplied by really just adds up, or not adds up to, but is a factor of 1, right? So this, and this, if you multiply all that together, you get 28x divided by 28x, which of course is just 1. So we multiply this whole thing here by 1, and that does not affect the answer. That doesn't affect the limit. So I hope that helps. Boy, this was all one section, and this is the second part of that section. So I think I'm gonna leave it at that. Well, okay, maybe one more example. This is something that might come up in the homework. All right, so give me a second. Okay, one more example. Getting a little tired, but I think this might be an important one. So we talked about instantaneous velocity before, again, very informally. But now, we can think of this as sort of the definition. The instantaneous velocity of an object with position s, and I know I used to call it x, but here we're calling it s, at a time t equal to a, is given by this formula right here. Right? V of a is the limit as t approaches a of s of t minus s of a divided by t minus a. Okay? And so if s is equal to this function here, 7t squared plus 4t, we want to find the speed, the instantaneous speed, at t is equal to 3. So that's the question. Right? And so in order to do this, we want to find v of 3, right, which is going to be defined as the limit as t approaches, a is 3 here, right? S of t minus s of 3 divided by t minus 3. Okay, so to find this velocity here at time t equals 3, we have to evaluate this limit. Okay, so how do we evaluate this limit? Well, first thing we should do, of course, is replace s of t here with this function. Right? S of t is given. It's going to be 7t squared plus 4 times t minus s of 3. Now, what's s of 3? We can do that separately up here. S of 3, just replace t with 3, right? So 7 times 3 squared plus 4 times 3. What is this going to be? Oh, let's do it here. This is going to be equal to 7 times 9, which is 63. Sorry about that. 63 plus 12. So 63 plus 12 is 75. So there we go. S of 3 here is minus 75. Or I'm sorry, S of 3 is 75, but we're subtracting that, right? Yes. Divided by t minus 3. And now I realize I didn't need such a long fraction here, but it's okay. All right, so how do we evaluate this limit? We've done problems just like this, right? We usually use x instead of t, but it's no different. Right? So notice that in the denominator we have a factor of t minus 3. So that means the numerator should also have a factor of t minus 3. So what's the other factor? Well, it's got to be 7t, and then, let's see, 25 times negative 3 is negative 75, so plus 25. Right? And if you, again, you can actually just do the division here. You can do synthetic division and get the same answer. So we have a 3 on the outside, right? And we have a 7, a 4, and a negative 75. So when you do the synthetic division, bring down the 7, right? 7 plus 0 is 7. 7 times 3 is 21. 4 plus 21 is 25. 3 times 25 is 75. And negative 75 plus 75 is 0. 0 is the remainder, right? This is 7t plus 25 is the quotient. Okay, so, right, if you're terrible at factoring, you could have done it that way too. Right. But now you see what we have to do here. T minus 3 divided by t minus 3 is 1. So the t minus 3's cancel. And now, there's no problem. To take the limit, as t approaches 3 of 7 times t plus 25, just plug in the 3. Oops, sorry, I'm doing this the wrong way here. Yeah, 7 times 3 plus 25, right, is 21 plus 25, right, which is 46. Oops, sorry, 46. 46. 46 what? Oh, I didn't give units here, so 46 whatever. Right, so yeah, in this case the answer is just 46. Just realize that in most problems we're going to give you units, right? So it might be 46, feet per second, miles per hour, meters per second. Yeah, so you should include units here, but in this case there are no units. It's just 45 units of distance divided by units of time. So some sort of distance divided by time, right? So meters per second usually, but yeah. So in this case, we don't need that. The answer here is just 46. But that's the speed. That's how fast we're going at time t equals 3 seconds. Okay? That's all it is. So that's, again, this example is really just calculating limits the usual way. You have to simplify the numerator, and that means factoring this as this. And then once you factor, you should be able to cancel one of the factors. In this case, it's the t minus 3. And of course, that's where you get your 0 divided by 0 from. Right? So once you cancel those, then that 0 divided by 0 goes away, and you get a nice number, 46 in this example. Right. So there we go. I hope that helps. Right? That should do it for this section. The next video we'll start a new section, and hopefully it won't be as long as this.